In this lecture, I'm going to review some basic properties of finite difference or finite volume methods in terms of accuracy, consistency, stability, and the CFL or Grant-Friedrich-Levy condition. This material is kind of scattered around a bit between chapters 4 and 8 mostly, but I'll go into a bit more detail here than is in the book. If you're interested in reading more about these topics, there's a lot of other books that go into more details on some of these sort of more basic ideas. In particular, I have a book on finite difference methods for ODEs and PDEs, and chapter 10 is devoted to the advection equation, but kind of builds on ODE stability and accuracy theory. So that's one source, but there's lots of other books that you might take a look at as well. So again, there's a difference between finite difference and finite volume methods, and mostly I'll be talking about the methods in CLAWPAC, which are finite volume methods. But for some of these basic ideas, it's easier to think about them in terms of finite difference methods. And as we've seen, simple methods like the upwind method can be viewed as either sort of method. And in the case of finite difference methods, again, we're thinking of approximating the solution of the PDE pointwise and approximating the derivatives by finite differences. And some of the ideas that we'll look at now in terms of truncation error, for example, are most easily expressed in that form. So if we look at the upwind method, whether we think of it as a finite difference or a finite volume method, it has this form on the top line here as an explicit numerical method. And this is sort of the form where we would implement it, where we're updating qi at time n to get qi at time n plus 1 based on fluxes computed based on the values at time n. So it's an explicit time-stepping method. But we originally derived this in the finite difference framework by discretizing the advection equation as this finite difference model and then rearranging things to solve for qi n plus 1. In terms of defining the accuracy, it's this form that sort of most closely mimics the PDE that we're going to use to define what we mean by the local truncation error. So the local truncation error of the method is obtained by taking the finite difference form that we have here and replacing qin by the true solution qi at q at xi tn, and replacing qin plus 1 by the true solution q at xi and time tn plus 1, and so on for these other terms. So qi minus 1 would be replaced by q at xi minus 1 tn, for example. So when we put the true solution of the differential equation into this difference equation, we no longer get 0. Setting this to 0 is how we defined our numerical method. But if we insert the true solution in there, we don't get 0. Instead, we get something that we call the local truncation error, tau, which is a function of the particular point. This should be tau of xi comma tn if I'm evaluating it at these points. And then the idea is that at least if we're looking at smooth solutions, we can use Taylor series to expand each of these terms. For example, q at xi tn plus 1, we can expand about q at xi tn plus delta t times the time derivative, half delta t squared times the second derivative in time, and so on. And we can use that to replace q at xi tn plus 1. And when we do that, we'll get a cancellation of this term with that term, and what's left over will be order delta t plus higher order terms, and we'll be canceling out a delta t eventually. Similarly, in the x displacement q at xi minus 1 tn, we can expand that as a Taylor series about q at xi tn involving delta x and derivatives of q with respect to x. So if we do those Taylor series expansions and insert them in there and simplify, then what we're left with, after we cancel out the terms that are common and divide by one factor of delta t and delta x, what we're left with is a sort of order 1 term, potentially qt plus uqx, plus a term that is first order in delta x and delta t, plus higher order terms, the dots in those Taylor series expansions, after dividing by delta t and delta x will give us things that are second order in delta x and delta t. Okay, so this order 1 term though it turns out to be exactly the differential equation, qt plus uqx, or it's the left-hand side of the differential equation. And we're assuming q is the exact solution of that, so that is exactly equal to 0. And so that order 1 term drops out, and we end up with a local truncation error that's the remaining part, which ends up being, well, the first term, after we drop the O of 1 term, the first term will be order delta x and delta t, and then I've also replaced the qtt term here, the second derivative in time, with u squared times qxx. And you can calculate that again from the differential equation, since q is the exact solution. If we take this differential equation, qt plus uqx equals 0, and we differentiate with respect to time, and also differentiate it with respect to x, and then use those two to eliminate the cross-derivative qxt term, you end up with this sort of wave equation, qtt equals u squared qxx. And so I've used that to replace the qtt up here, and then I've also factored out a delta x here, so that we end up with the truncation error as a constant, a delta x, a term that's proportional to delta x, and then there's a factor u delta t over delta x minus 1 times u qxx. How large this truncation error is in practice will depend then on both how fine our grid is in both space and time, how small delta x and delta t are, and also on how rapidly the solution is varying, because the derivative of the true solution comes in here. So for a rapidly varying solution, we'll have a much larger truncation error with a given delta x and delta t than we would for a smoother function. Yeah, so there's that local truncation error again. And often for hyperbolic problems, we'll assume that if we're trying to get a better solution and refine the grid and hope that we get convergence to a true solution, we'll often assume that we hold delta t over delta x constant, so that we're refining in space and time at the same rates. And for hyperbolic equations, that typically makes sense in terms of the time scales and space scales. So if we want to refine by a factor of 2 in x, we'll also be refining by a factor of 2 in t. And if we make that assumption, then this factor u delta t over delta x here, which is called the Courant number that we'll talk a lot more about in a moment, would be a constant. And so we have basically some delta t times some constant as we refine the grid. And so the method is said to be first order accurate in space and time, assuming we're refining in time and space at the same rate, because this local truncation error depends on the first derivative, or sorry, the first power of delta x. If it were proportional to delta x squared, then it would be a second order method. But here it's a first order accurate method. Now, what we've shown so far is just that this local error, if we sort of expand things in Taylor series, that it looks like it has a local error, a local truncation error that's first order. But then the really interesting thing is to try to prove from that the method actually converges as you refine the grid. And for that requires something else. It requires the concept of stability that we'll talk more about. But if the method has an appropriate form of stability, then as we refine the grid in space and time, the idea is that if the method is first order accurate in terms of this local truncation error that we can calculate by simply doing Taylor series expansions, then you can also show that the global error will be first order accurate, meaning that if we look at what I'll call capital E of xt, the difference between our numerical approximation at some xt and the true solution at that same point, as we refine the grid. So as we refine the grid, I'm not really precisely defining what this capital Q is, but it's a function that sort of represents our numerical solution, maybe piecewise constant in space and time on the grid that we are looking at. If we fix the point xt and refine the grid, then the hope is that at each point, at any xt point, the approximation that we have in the neighborhood of that point is converging to the true solution. And the hope is that the difference between those two, the global error at this particular point at some fixed time, will also be order delta t, or order delta x rather here. which is the same as order delta t if we keep delta t over x constant. But it would be first order accurate also in terms of this global error as we refine the grid. But to get from this local order 1 to a global order 1 requires some form of stability. And the reason is that in order to get up to a fixed time as we're refining the grid, as we refine in time, the number of time steps that we have to take is going to infinity. So it's not just a single step we're looking at as we do in the local truncation error, it's the accumulation of many, many steps, and the number of steps we have to take in principle goes to infinity as we refine the grid. So it's not necessarily easy to prove from the local accuracy that we also have this sort of global accuracy. Moreover, those Taylor series expansions are all assuming that the functions are nice and smooth, and we can expand the solution in terms of Taylor series. What happens if we have a discontinuous solution instead? As we often do with hyperbolic problems, if there's a discontinuity in Q, then those Taylor series expansions simply aren't valid near the discontinuity, and even the local error is not going to be order delta x as we refine the grid. And it's not at all clear what happens with the global error. So the sort of result I just mentioned on the previous slide was that we could hope for smooth solutions that this global error is actually going to zero pointwise at every point, that this might be converging to zero for all fixed x and t as we refine the grid. We might hope that's true, and for smooth enough solutions you can prove that that sort of thing is true. And if that were true, then that would also mean that if we look at the infinity norm of the solution at a fixed time, or the max norm, which is defined for a fixed time, the max norm is defined to be the maximum over all x in whatever interval we're looking at. If we're doing a boundary value problem, or if we were doing the Cauchy problem, we might have this over all of space. But we would define the infinity norm or the max norm to be the maximum value of the error over that particular interval at this time t. And if we had a pointwise convergence at every point, then we would also expect that this max norm would be going to zero. But in the case of discontinuous solutions, that's typically not true. We can't expect that it goes to zero at every point. Near where there's a discontinuity, no matter how fine we make the grid, if we have a discontinuous solution, we'll often find that maybe we're approximating it very well up here and down here, but there's going to be probably some point in the middle where things are smeared out at least a little bit, and the pointwise error at that point is going to be large, and refining the grid isn't necessarily going to make it better. It might make it better, make the average error much better, but there'll still be some points where it's not converging at all. And so you can't expect pointwise convergence or max norm convergence typically for discontinuous solutions. So typically the best you can hope for is some sort of convergence in a norm that involves integrating over the interval that you're looking at, the 1 norm or the 2 norm or some other such norm. For conservation laws, a sensible norm to use is often the 1 norm, which is defined here as the integral over whatever interval we're looking at of the absolute value of the error. Or if we were looking at a system of equations, it would be the integral of some norm of the error, which would be a vector, one of the same length as the number of equations in the system. But if we just look at a scalar problem, then it would just be the integral of the absolute value of the error. Or in terms of our numerical approximation, if QIN is an approximation at time n, which corresponds to the time t that we're looking at here, then we would be looking at summing up the absolute error at each grid point, summed over all the grid points, multiplied by delta x, which corresponds to the dx in the integral. And what we would hope is that as we refine the grid, so of course the n will have to change as we add more and more time steps, and the number of spatial points that we're summing over will increase as we add more and more spatial points. We would hope that this might converge to zero. And if we have smooth solutions, then typically we expect this to converge at the same rate as the local truncation error, order delta x, for example, for the upwind method. For discontinuity, though, or near discontinuity, because of the issue I just mentioned, there's always some points near the discontinuity where things are smeared out, and the number of such points shrinks as we, or maybe doesn't shrink, but the delta x corresponding to those points shrinks, and if the number of bad points stays finite at least, then you could hope that you still have convergence in this norm, but often you don't have convergence at as good a rate as you do for smooth solutions. So in particular for discontinuous solutions, as we'll see later, often we can expect even in the one norm that we don't have order delta x convergence. We have something like order the square root of delta x, which goes to 0 more slowly than delta x. So if we refine in space and time by a factor of 4, the error might only decrease by a factor of 2 if we have this sort of error rate. But again, it depends very much on what norm you're using and exactly what the problem is, what sort of error rates you get. So this is just kind of a hint of some of the issues that we'll look at in more detail later. Here's just an example. This is, I think, in figure 6.1 in the book, something similar to this, where various different advection schemes are compared. And in the ClawPack apps repository, there's the code that was used to generate these plots. But what's being solved here is just the advection equation with speed u equals 1, so it's just qt plus qx equals 0 on the unit interval from 0 to 1 with periodic boundary conditions. So it's translating to the right, it goes out the right boundary, but comes back in. And at time 1, it should be exactly back to where it started. So the true solution at time 1 looks exactly like the initial data, which is shown here. The blue dots here are the initial cell averages or pointwise values, depending on what sort of method you're thinking about, with 200 grid cells. So we have a smooth Gaussian plus we have a square pulse. And so what happens if we use just the upwind method with this initial data and run it out to time 1 so that it should be back to exactly what it started, is that you might see something like this. Exactly what you see depends on the ratio between delta t and delta x. We'll talk more about that later. But typically it will get smeared out in this way. And we see a smearing of the discontinuity, but we also see that even the relatively smooth Gaussian is not very well represented. And that's because the first order upwind method is not a very good method. It's not very accurate. This is with 200 cells. If we double the number of grid points, then we would expect the error to get better. In fact, where things are smooth, if it's first order accurate, we would expect that doubling the number of cells and doubling the number of time steps that we have to take to get up to this time, the error should go down about by a factor of 2. And if we run this with 400 cells, what we see is that in the smooth part, over here where the Gaussian hump is, that the error does go down by roughly a factor of 2 near the peak of that Gaussian. Let me toggle between those two. But if you look at points near the discontinuity, there's going to be points where the error is very close to 1/2. It should be 0 and it's close to 1/2, or it should be 1 and it's close to 1/2. And as we refine the grid, there's always going to be points near that interface, near that discontinuity, that are off by 1/2. So we don't get pointwise convergence. And if you calculated the one norm of the error, you'd see that it goes down because of that square pulse with the discontinuities. It goes down like the square root of delta x. Okay, a couple other basic concepts. We say that the method is consistent if the local truncation error goes to 0 as we refine the grid. So again, the local truncation error is based on just the Taylor series expansion of the form of the difference equation that looks like the PDE. And so we certainly hope that those terms go to 0. When we do the Taylor series expansion, remember the order 1 terms should cancel out, and we should be left with things that are order delta x and delta t that'll go to 0. But you could conceivably have a method where it was consistent, but it went to 0 at a rate even slower than delta t and delta x, like the square root or something. But as long as the local truncation goes to 0 as we refine the grid locally, we call it consistent. What's also interesting is to look at what's sometimes called the one-step error, which is if we take the differential equation or our finite difference approximation and write it more in the form where we're updating the solution based on the previous value. In other words, we multiply through by delta t, so we look at delta t times tau, and then what we have is the difference, because we put the true solution into the difference equation, we have the difference between the true solution at time t plus delta t and the numerical approximation that would be generated based on the true solution at time t. So if we think of applying the upwind method to q at xt by taking q of xt and subtracting u delta t over delta x times q at xt minus q at x minus delta t, this is basically the upwind applied to the true solution as initial data. That gives us not the true solution at the next time step, however, because of the truncation error. What it gives us, though, is exactly delta t times tau, based on the way that we define the local truncation error tau. So this is larger, or smaller rather, by a factor of delta t than the local truncation error. However, if we think of time stepping, then we can think of making an error that has roughly this magnitude in every time step. And to get up to a fixed time capital T, we have to take roughly t divided by delta t time steps. So as we refine the time step, the number of time steps we have to take is going to infinity, like capital T over delta t for a fixed time capital T. So that suggests that if we look at the global error at time capital T, then we're going to be, we could approximate that by the number of time steps we take times the error we make in every step. And when we do that product, the delta t's cancel out, and so we get something that looks like t times tau. So that suggests that, again, the global error, E, is roughly like the time t multiplied by the local error. So that's why I said that if we have a local error that's order delta x, then we can hope that the global error will also be order delta x, because it's only multiplied by this constant t that's independent of the grid as we refine the grid. Or more generally, if the local error is order delta x to some power p plus delta t to that power, then we can hope from this argument the global error will also be exactly the same order, and we would call the method pth order accurate. You can also have methods where it's maybe order p in space and order q in time. They don't necessarily have to be the same, but the same argument would show that whatever order we have in the local error, we would hope that the global error has the same order of accuracy. And so we hope that by doing these Taylor series expansions and calculating the local truncation error, we can use that to also estimate the global error. The problem with that is that as we refine the grid, again, we have to take more and more steps to get up to this fixed time. And it turns out that there's another big concept here called stability. And in order for this to work, we not only need this consistency, but we also need stability of a suitable form so that we can take this limit of taking more and more time steps to get up to the fixed time that we're interested in. And so this sort of equation that's written at the bottom here is what I often call the fundamental theorem of numerical differential equations. Consistency plus stability equals convergence. Typically, you need both consistency, that locally you're approximating the differential equation well, and stability, which says that you can take many steps and let the number of steps go to infinity as we refine the grid, and you still have reasonable behavior. And if you have both of those properties, then you can show that the method converges to the right solution at a fixed time as you refine the grid. And similarly, if a method is convergent for a wide class of initial conditions, then that means that it must be consistent and stable, typically. So we'll talk more about this a little later, but this is sort of the key idea that we need both to look at how well we're doing locally, but also how well we can do when we iterate in time. Now, for a conservation law or a system of conservation laws, there's kind of a special definition of consistency that we'll also be looking at later. But in the case of a conservation law, if we write things in conservation form, as we've seen before, where we take QIN and update it by a difference in fluxes at the left and right edge of a cell to get QI at time n plus 1. Remember, this is called conservation form because if we sum this up over all the grid cells, these internal fluxes cancel out, and we can show that the solution value is being conserved as it should be. For this particular form of a numerical method, if you rewrite this sort of in terms of what looks like the differential equation, the qin plus 1 minus qin divided by delta t plus 1 over delta x times the difference in fluxes. What we need is that difference in fluxes divided by delta x is modeling the derivative of f with respect to x properly. And it turns out what we really want for proving convergence in some cases, also when we have shock waves involved or other discontinuities, is that we want these numerical fluxes at each edge of the grid cell to be defined by some numerical flux function that I'll call script f, based on the data to the cell in the cell to the left of the interface and the data to the cell in the cell to the right of the interface. That numerical flux function, we'll see many ways to define numerical flux functions as we go along, should have the property that if we evaluate script f with both left and right states being some q bar, then this numerical flux simply reduces to the flux f, the true flux that defines the conservation law. That's a natural sort of property. If you have the same state on both sides of a Riemann problem, then you expect the solution won't change, and so the value at that interface as you go forward in time will remain q bar, and so the flux at that interface should just be f of q bar. And we also need some continuity as our left and right states approach q bar. And it's not enough to just be continuous, we actually need Lipschitz continuity, which means that if we look at the difference between the flux for an arbitrary QL and QR and the true flux evaluated at some q bar, in the case where QL and QR are close to q bar, then as QL and QR approach q bar, that difference should go to 0. But to be Lipschitz continuous, it has to go to 0 at a rate that's bounded by some fixed constant c times the difference between the left and right states and this value q bar. So it says that it's not only continuous that this difference goes to 0, but it has to go to 0 at least as fast as the differences in the left and right state are vanishing. And this should hold for all QL and QR in some small neighborhood of q bar, in particular as if we think of QL and QR converging to q bar, then the numerical flux function has to converge to this value, but it also has to have this Lipschitz continuity property. And that we'll see later will be important in proving convergence of conservative methods for certain conservation laws. So as a simple example, if we just look at the upwind equation, when u is positive, then the numerical flux function is simply u times the value of q to the left of the interface. So script f of QL, QR is u times QL. And that function, of course, if we plug in the same value q bar twice, that'll just be u times q bar, which is in fact f of q bar. So it satisfies that. And if you look at this Lipschitz continuity condition, it's satisfied if we choose the constant c to just be u, which is a constant in the advection equation we're looking at. So that's certainly a consistent flux. Just a few other examples. Again, this is the general form of a conservation law with some numerical flux function script f. We just looked at the upwind method. For nonlinear problems, I just wanted to point out that this constant c that is used in defining what we mean by Lipschitz continuity can vary with q bar. So for example, if we look at Berger's equation, where f of q would be a half q squared, then if you think about the Lipschitz continuity condition, and if we use, say, the upwind flux, well, assuming q is positive, the upwind flux would again be looking at the flux to the left of the interface, which would just be a half ql squared. If you look at how that converges to 1/2 q bar squared as ql approaches q bar, that is Lipschitz continuous, but you have to take the constant c to be roughly q bar, or a little larger than q bar, because your qr might be a little larger than ql, and you need this to hold in some neighborhood. But basically you can if you're thinking of a fixed point q bar, then you can choose a c or if you can choose a C such that you have this Lipschitz continuity property satisfied, then we would say that the flux is Lipschitz continuous. Here's an example for a system of equations. If we look at the linear system qt plus aqx equals 0, then if we look at Godunnov's method, which is, remember, the natural generalization of the upwind method to a system of equations, then the numerical flux function comes from splitting up the matrix based on its positive and negative eigenvalues, and it's the A plus matrix times QL plus the A minus matrix times QR. If we evaluate that F with both QL and QR equal to Q bar, then we would just get A plus Q bar plus A minus Q bar, but A plus plus A minus is the original A, so that's just A Q bar, which is F of Q bar. And it's also Lipschitz continuous. In this case, if this is a system of equations, the Lipschitz continuity requires looking at the norm of QL minus Q bar and QR minus Q bar, but if you think about that, you can show that it's Lipschitz continuous with the constant C being basically the matrix norm of the matrix A, corresponding to whatever norm we're looking at measuring the vectors in. So that's also a consistent flux. Here's a flux that's consistent but not very useful for this particular problem because the resulting method is not stable. But it's a very natural thing to think about, that is to use a centered flux. If we, for the case of the linear system, rather than splitting up A into A plus and A minus, we could just split A into a half A and a half A, or look at defining the flux as A times the average of Q left and Q right. And that generalizes very naturally to a general system of conservation laws. Why not just define the flux to be the average of the flux in the left state and the flux in the right state? That's a very natural way to define the flux at the interface between the two cells. And it wouldn't be looking at which direction waves are going, it would just be averaging the flux on the two sides. It's much simpler, but it's also not very useful because it's, even though it's consistent, you can show this is Lipschitz continuous, at least as long as the original flux function F is a Lipschitz continuous function. But if you put this flux into this method up here at the top, then at least if you assume this delta t over delta x is fixed as we refine the grid, it turns out that this method is always unstable, no matter how small you choose delta t over delta x. If you fix that as you refine the grid, it will be unstable. You can use this method if you let delta t go to 0 faster than delta x, but for the kind of methods that we're looking at, well, we can do much better than this. So even though this is a very simple sort of flux and it's consistent, it's not stable, and therefore the resulting method would not be convergent if we fix delta t over delta x. So consistency is just one requirement. We also need some form of stability in order to get convergence. And again, I won't go into this too much more detail now, but just to kind of remind you that for other sorts of ODEs and PDEs, there's similar theorems of this sort. For ODEs, this often goes by the name of Dahlquist's theorem. And for an ordinary differential equation, typically what you need in the way of stability is something called zero stability, which you can think of as being simply looking at the ordinary differential equation Q prime of t equals 0. It turns out that looks like such a simple equation because the exact solution is just constant. But if you apply certain methods to that equation, it doesn't necessarily behave well. But it turns out that if you can show that your method behaves well on that equation, then it also is stable more generally, and that together with consistency can give you convergence. For linear PDEs, there's something called Lax-Richtmeier stability, which involves uniform power boundedness of a family of matrices that come up when we discretize a system with more and more equations in a linear case. And there's a well-known Lax equivalence theorem that says that this sort of stability plus consistency is necessary and sufficient for proving convergence on linear PDEs. For conservation laws, in the case of a scalar conservation law, even when it's nonlinear, there are ways to tackle the stability. There's a different form of stability that's needed here, And there's a couple of different varieties that we'll look at. Mostly we'll look at this idea of total variation stability, but there's also a lot of work being done on entropy stability for looking at proving that numerical methods converge for nonlinear conservation laws. Unfortunately, for systems of conservation laws, it becomes much more difficult to get a handle on what the right form of stability is, and very hard to prove convergence of numerical methods. It's even hard to prove the existence and uniqueness of solutions of the PDEs in themselves. In the case of nonlinear systems of equations, this has been a huge topic of research for the past several decades, and certainly some progress has been made on this, but it's still, there are many open questions there. So we won't dive too deeply into stability for systems of conservation laws. Fortunately, the methods that we look at often work very well, even if we can't mathematically prove that they converge. So let's go back to looking at stability for the upwind method. And again, I'm not going to prove it here. We'll look at that in a bit more detail later. But I wanted to go back and mention this Courant number, or CFL number as it's sometimes called, U delta T over delta X, that comes into the definition of the method. It also comes into the stability condition, as we'll see. This is called the CFL number. After Courant, Friedrichs, and Levy wrote a paper in 1928, actually, which was on the existence and uniqueness of solutions to PDEs. And the way they tackled that to prove that certain PDEs had a unique solution was to write down a numerical method, basically, and then prove that the numerical method converged as you refine the grid, and show that the limiting solution that you got from that numerical method, in principle, would be a solution of the PDE. So they basically did the convergence proof for a numerical method, even though in 1928 there were no computers around, so people were not really using numerical methods for partial differential equations at all. So it was a numerical method for a theoretical result. But it was a very important, influential paper in the study of numerical methods and stability that was recognized much later when people started trying to do computing, that this ratio was crucially important for stability of even the simple advection equation. If we think about the upwind method in the interpretation of Godunov's method that we've looked at as a finite volume method, then if we think of it in terms of waves propagating into a cell, then remember that in a single time step, U delta T is the distance that a wave propagates from the interface into a grid cell. And if the denominator here, delta X, is the width of that width of the grid cell, then this ratio, U delta T over delta X, tells you the fraction of a grid cell that the wave is moving through in a single step. And so if you think about it that way, then it makes sense that you need this number to be less than 1 if you're using a method that's only looking at the two states on either side of the interface. Because if waves start going more than one grid cell on a single time step, then they're going to be influencing places farther away where we haven't perhaps taken into account enough of the initial data to take a larger time step. And in fact, for the upwind method, well, this form of the upwind method where we're using the difference qi minus 1 is assuming that the velocity is positive. And you can show that this method is stable only if this Courant number is between 0 and 1. It can't be negative. Of course, delta T and delta X are always positive, but that means then that U has to be positive also. If U is negative, then we have to use a different version of the upwind method where we're using Qi plus 1 instead of Qi minus 1. So associated with this idea of the Courant number, there's something called the CFL condition, which came out of this same paper by Courant, Friedrichs, and Levy, which is really a necessary condition for stability. And a more general way of sort of phrasing it that applies also to the advection case we were just thinking about is that the true solution, if we look at some fixed point xt, the true solution at that point typically depends on the initial data over some set of values, some domain D that depends on capital X and capital T. So in the case of the advection equation, since the solution at capital X, capital T is simply the initial data at capital X minus UT, then the true solution at this point really depends on the initial data only at this one point, X minus UT. So the domain of dependence of the true solution at xt is a single point, X minus UT. That's kind of a special case. This advection equation is very special. Many times differential equations, the solution at one point depends on the initial data many places, or even maybe over an entire interval, or maybe even over the entire real line. So for example, the acoustics equation, we would expect the solution at each point depends on the initial data at 2 points, because there's a left-going sound wave and a right-going sound wave that both reach this point at a given time. But anyway, once we've defined this domain of dependence, the idea of the CFL condition is that the only way a method can be convergent is if can only be convergent if its numerical domain of dependence contains the true domain of dependence, at least in the limit as delta t and delta x go to 0. So the numerical domain of dependence, I'll explain in the next couple of slides, but that's sort of what set of values from the initial data affect the numerical solution at this point xt. We know what the true domain of dependence is, but when we do computations, we're computing a value there, an approximation there that's based on some set of initial data. What set of initial data are we using for that approximation? And that set of data we're using for the approximation had better include the point that is actually the true domain of dependence in this case. So this gives a necessary condition, but not necessarily, it's not sufficient for stability, but it's definitely a necessary condition for stability. Sometimes it agrees exactly with what the stability bound is for some methods, but there are methods for which the CFL condition is satisfied, but the method is still unstable. And we'll see examples of that as we go along. So here's the idea of sort of the numerical domain of dependence. If we start with this grid on the top here, and we're using a 3-point method, which means that the value that we compute at one point depends on 3 values from the previous time step, the same point and the points to the left or the right. It might use a different set, but suppose this is its stencil, that this value depends on these 3 values. Then each of those values in turn depends on 3 values at the previous time step. This one depends on these 3, this one depends on these 3, and so this point really depends on 5 points at the initial time. And then if we refine the grid, if we refine both delta t and delta x at the same rate, cut them both in half, for example, then if we're still using the same 3-point method, now this point depends on these 3, but those depend on these 5, which depend on these 7, which depend on these 9. And so there's more points of the initial data that are required for the approximation here. But they're in space, they're sort of filling out the same set of points. They're just a denser mesh on that set of points. So here's another sort of picture down at the bottom where we're envisioning a particular point, and this is over a single time step of length delta t, and again the 3-point method, so this value is computed based on these 3 values. Okay, but now suppose that this CFL condition is violated. Suppose that u delta t over delta x is not less than 1, and so when we trace back this characteristic, this is the curve x that's moving at speed u. When we trace back this characteristic, we reach a point that doesn't lie between these points where our numerical approximation is calculated. Then the numerical approximation is based on these 3 points. The true solution here is based on the initial data at this 1 point. Okay, and now the problem is that even if we refine the grid, and we refine at the same rate in x and t, so we cut x in half and we cut t in half, but we're using the same 3-point method, or we cut it down again by a factor of 2, then no matter how fine we make this, if this characteristic is hitting back here at a point that's outside of this triangle of points that are being used in our numerical approximation, then no matter how fine we make the grid, even as we go to delta x and delta t going to 0, The numerical solution at this point is going to be based on the initial conditions only over this interval where we're sampling the initial data, whereas the true solution at this point is based on this one point over here. And so I could change the data in such a way that I've changed the true solution without changing the numerical approximation whatsoever, or vice versa. And so there's no way that the numerical method can be converging to the true solution of the differential equation when it's using data that's potentially completely independent of what the true solution of the differential equation is. So that's kind of the picture of why the CFL condition makes sense. So if we have a 3-point method, then we have this condition that the absolute value of u delta t over delta x has to be less than or equal to 1. The characteristic could be going in either direction, to the left or the right, but it has to be have a slope so that it falls within this triangle as we go back in time. So here's a few stencils, the sort of picture of what value at the advanced time we're using what values at the previous time we're using to compute the value at the advanced time. So for example, in the upwind method, if u is positive, we're computing a value here based on this value and one value to the left. So we have this sort of stencil. And we've seen that for the upwind method, for example, we have this stability condition, that is the CFL condition for that stencil, as we refine the grid if delta t over delta x is fixed. If u were negative instead of positive, then instead we might use an upwind method that looks like this one, where our stencil is looking to the right instead of to the left. And then it turns out the CFL condition says that u delta t over delta x has to be between -1 and 0, so that when we trace a characteristic back here, it lies somewhere between those 2 points and doesn't lie either to the left or the right of that interval. The 3-point method we've already looked at as this condition, but you could have more complicated stencils, for example, an upwind sort of method where it uses 2 values to the left as well as the value at grid cell I to compute the new value. And then the CFL condition would say that u delta t over delta x has to be between 0 and 2. The characteristic when we trace back has to lie somewhere in that triangle. It could go as far as 2 delta t or 2 delta x away from the point that we're at. Again, that doesn't guarantee that a method with a stencil will be stable, but that's a necessary condition for stability. Finally, the bottom one shows an implicit method, a stencil for an implicit 3-point method. So again, this is at time tn plus 1, and this is at time tn. So what does this figure mean? It means that the solution or when we write down our difference equations, we're using not just the value we're trying to compute at time n plus 1, but also its neighbors at time n plus 1, and those are coupled together with 3 values at time tn. And so typically that means it's an implicit method, which in order to actually solve it numerically, you don't have an explicit method for each of these values. Instead, all of these values are coupled at all points, and you end up with a system of equations that happens to be solved simultaneously for all values at time tn plus 1. So that's an implicit method. If it's a linear problem, then that might just give you a tridiagonal matrix of equations because each point is only coupled to its 2 neighbors, for example. In more dimensions, it might be more messy. Because of the fact that everything is coupled and the only way to compute things at the next time is to solve a linear system that involves all of the data at the previous time, the CFL condition for this method isn't providing any restriction because we're in essence using all of the data at time tn to calculate each value at time tn plus 1. So in principle, we're taking into account all of the data, no matter how large our delta t over delta x is. So that an implicit method doesn't have a CFL restriction. It still might have some stability restriction, might only be stable for certain values of delta t over delta x, but the CFL condition at least is not imposing anything. So implicit methods are more typically used for parabolic equations rather than hyperbolic equations. So, for example, the heat equation or convection diffusion or fluid dynamics with viscosity. Because for parabolic equations, if we look at the domain of dependence of a point, it is the entire axis. For a hyperbolic problem, we can just trace back characteristics, and we have a finite number of points that determine the solution. But for a parabolic equation, the solution at every point initially can influence the solution everywhere. So for example, if we look at the heat equation, even if we take initial data that's a delta function or localized at a single point and zero everywhere else, then the solution is a Gaussian that's non-zero everywhere. That delta function immediately spreads out to something that's non-zero everywhere. It's exponentially small away from the origin, but it's still non-zero everywhere. And this is the Green's function for the heat equation. So if you had initial data that was only on some finite interval, then integrating this against the initial data would give us the general solution, and that would also show that the solution, even if you have initial data that's only non-zero on an interval, the solution will be non-zero everywhere immediately. So the domain of dependence is the entire real line. And so for a parabolic equation, the CFL condition requires either that we use an implicit method like we were just talking about, which through its coupling of all the points at the advanced time gives us the CFL condition being satisfied. Or if we want to use an explicit method, for example, the kind of method we were looking at extended to a parabolic equation, then we can't let delta t over delta x be fixed as the grid is refined, because that's always going to give us sort of a finite domain of dependence. Instead, you'd have to let delta t go to zero faster than delta x, so that as you refine the grid in space, you're adding more and more time steps, and then your domain of dependence would be finite for any particular grid, but as you refine further and further, that triangle would be spreading out more and more, and you'd eventually, in the limit at least, be covering all of the data that you need for the true solution. So parabolic equations are typically more complicated to solve in that you often have to use an implicit method in order to get a method that's both stable and computationally efficient. Even though implicit methods are more work per time step, they're often more efficient than using an explicit method with the really sort of tiny time steps that you often have to use for explicit methods in parabolic equations. Okay, so finally, just to wrap up here, the idea of the CFL condition extends to linear hyperbolic equations like acoustics or other more complicated systems. If it's linear, then we know that we can diagonalize and get eigenvalues, which give us the wave speeds and the characteristic variables, and that we can write the solution at any time in terms of the initial data, tracing back these M characteristics. So if we look at these same stencils we looked at before, but now look at it in the context of a hyperbolic system, the CFL conditions look almost identical, except that now what we require, for example, if this is our stencil, then we require that lambda p times delta t over delta x should be between 0 and 1 for all p going from 1, 2, 3 up to m, for example. So if we have a system of m equations, then all of these characteristics would have to trace back to lie within this triangle in order to have something that is behaving properly. If we have a three-point method, for example, then all of the characteristics have to trace back. Some might be negative, some might be positive, but they all have to trace back to within this triangle. So lambda delta t over delta x has to be between plus and minus 1 for each equation in the system, and so on.